Let's jump into the lab environment and spin up the resources we need to get started. Head down to the video description, click the Killercoda Interactive Lab link under Resources and Links section, and you'll land right here. On the left pane, you'll find the step-by-step instructions. On the right, you have an interactive Linux terminal where you will create our Kubernetes resources, apply network policies, and test our setup. Here's the plan. We'll create 3 namespaces, frontend, middleware, and backend. Inside them, we'll deploy 3 NGINX pods named web app, middleware, and MySQL respectively. We'll start with the fundamentals of the networking policy and build our skills step by step. By the end of this series, we'll have a completely locked down cluster with controlled end-to-end traffic that looks like this. As you can see, external users access the application via a service tied to the web app pod. The middleware pod mediates the communication between the web app and MySQL pod. Under no circumstances can the web app pod talk directly to the MySQL database, nor can the traffic flow in the reverse. Additionally, we have an external backup service outside the cluster that communicates strictly with the MySQL pod. We'll achieve all of this security using Kubernetes Network Policies. Now, hit that start button and let's get building. You'll see all the necessary commands listed on the left. You can type them in manually or simply click on them to run them directly in the terminal. Let's start by creating our 3 namespaces, frontend, middleware, and backend. Next, we'll deploy an NGINX pod into each of these namespaces, naming them web app, middleware, and MySQL respectively. We are using the lightweight NGINX containers here to keep things simple and avoid the overhead of setting up a fully blown application, since our main focus today is strictly on the network policies. Let's give it a second for these pods to initialize. And perfect, they're all up and running. Now, as we have covered earlier, Kubernetes automatically assigns unique IP address to every pod in the cluster. We can verify this by running the command here. Right there, you can see the dedicated IP address for all 3 pods. Let's run a quick curl command against one of these IP addresses to test the connectivity. Curl followed by the IP address, and that works. Notice how it returns the welcome to NGINX. So that's the standard default landing page. Now, since every pod returns this exact same message, let's customize each index page so we can easily tell them apart. We'll set the web app pod to respond with the front end, the middleware pod with middleware, and the MySQL pod with backend. Let's run these commands to update the HTML files. So this will update the index page of the front end, this one with the middleware, and this one with the backend. Now let's test this by running the curl command against the web app pod's IP address again. And there it is. It returns frontend as expected. Now, for the big question, can these pods talk to each other across namespaces? So to test this, we can exec into one of the pod's terminal and attempt to run the curl command against another pod's IP address. Let's see if our web app pod in the frontend namespace can reach the middleware pod in the middleware namespace by running this command. So it returns middleware, which is an indication of success. Now let's test this if the middleware pod can reach our MySQL pod in the backend namespace. And again, we got our backend response. So manually testing every single pod to pod connection takes time. So I have put together a quick helper script to speed things up. Simply click on the run validate connectivity.sh to test every path automatically. And here's how to read the output. First, you'll see the exact command executed under the hood to validate the connectivity. A green check mark means the source pod can connect to the destination pod successfully. A red X means the connection timed out or was blocked. Looking at the script's output, every single connection succeeded. This proves that out of the box, our pods can communicate freely across the entire cluster without any restrictions. Notice how we did not touch a single network config or manage routing tables. All we did was create namespace and deploy pods. Kubernetes handled all the networking and IP provisioning automatically. This is Kubernetes' default flat network model in action. While this is open, frictionless setup makes the development easy, it also means that without custom network policies, your entire cluster is completely exposed to security threats. Up next, we are going to fix this open setup, lock down our cluster, and build a truly secure Kubernetes environment. See you in the next.